At the beginning, we will follow quite closely the textbook. And as I have explained this week on Monday, we will learn actually some things you have already learned in high school. But we will discuss maybe some points, or I will stress some points which haven't been emphasized before. Now, since you have learned most of the things I'm going to teach you today and also maybe next week on Monday, I think I can go on a little bit more quicker. Now, the first thing, as I have already roughly explained last time, are the so-called exponential functions. Now, this is chapter 1.5 of our textbook. You all know what an exponential function is. You have learned this already in high school. So one example for an exponential function is, for instance, the function 2 to the x. Okay. Or more general, you choose any number for 2. You replace 2 by any number which is positive. So more general. Where a is larger than 0. Now, maybe just for the English at the beginning, okay, so this is called the base here. This is called the exponent. And we read this a to the x. I explained this already last time. Now, last time I already asked you, okay, in high school, how have you defined this function? Now, the definition is very easy for the case where x is a positive integer, because in this case, okay, you define now in general a to the x just as a times and so on times a, where you have here x terms. Then you extend this definition to x is equal to 0. So in this case, by definition, a to the 0 will be equal to 1. And then you further extend this definition to negative numbers. Okay, so if you have a negative number, then a to the x, you can define it. So a to the minus x is already defined here. So you can define it as 1 over a to the minus x. Now, if x is irrational, okay, so in particular, if we can write x as p over q, where the denominator, so this is called denominator, this is called the numerator, where the denominator is larger than 0, then you define a to the x as the qth root of a to the p. Okay, and now a to the p is already defined because p is either positive, negative, or 0, and you have the definition already here. And of course, you know that if you have a fraction like 1 over 2, so maybe you just have heard in English we read this p over q. Okay, if you have a fraction like 1 over 2, then you can also write the same fraction as 2 over 4. And because of properties of the root function and because of this definition, no matter which representation you choose here, you will always get the same number here, which is important, of course. Now, this is quite clear. This you have learned in high school, maybe long ago. But I stressed already last time. Now, the problem we have is, okay, how to define the function for irrational numbers. For instance, if x is equal to the square root of 3 or something like this. Now, this problem actually is not so easy to resolve. Maybe you have, I don't know how you have defined it in high school, but I will make a definition today. But this definition is not precise. And we will accept this definition for a long time. And then maybe in 2 months, I will precisely define what the function a to the x is. So at the moment, you should be aware that this is not so easy to define. Now, just to give you a... So are there any questions to this? No. Okay, so what is left is to define the function, for instance, for if we take a space 2, okay, for instance, to define 2 to the square root of 3, okay. Now, how to define this function? I have already explained this a little bit last time. So one way would be as follows. Okay, so we have already defined the function 2 to the x for x all rational numbers. Now what you could do is to plot the graph of this function. Of course, you will not be able to do this really. Okay, if you use software, also software is not be able to do this. But if you imagine this, that you just plot the graph of this function for x being a rational number, okay, what you will get is something which is dotted. You will have many holes, because we know that here you have many irrational numbers. But already from this graph, you get already an idea how to fill the holes. Namely, you see that if you just look at this function here, the function is increasing, okay, just for rational x. And now the way you are going to fill the hole is such that the function has this property for all x, so that the function remains increasing. Now, this, of course, is not a very good, very precise definition. Okay, because obviously, if you want to prove some basic properties of this function, you cannot use such a definition. But it's one way you can do it, and for the moment, it's enough for us. Okay, so for instance, if you want to know 2 to the square root of 3, okay, you just use this property. So you know that square root of 3 is, you know that square root of 3 is larger than 1.73 and smaller than 1.74. Those two numbers are rationals. And now, because of these increasing properties you want to have satisfied by this function, you immediately get that 2 to the square root of 3, which is not defined yet, has to be larger than 2 to the 1.73 and smaller than 2 to the 1.74. And so here you get a lower bound. Here you get an upper bound for this number we haven't defined yet. And if you make this lower and this upper bound better, then you will get here a smaller range. And in this range, you have to, actually, if you really want to define it, you have to prove there is only one number, which is between. So if we go on like this, if we add here more precision, we add one more digit, 1.732, and smaller than 1.733, then you get the same, 2 to the 1.732, smaller than 2 to the square root of 3, smaller than 2 to the 1.733, and you go on like this. You will find out that this sequence of numbers is getting larger and larger. This sequence of numbers is getting smaller and smaller. And now what you actually have to prove is that there is exactly one number, which is larger equal than all of those numbers, smaller equal than all of those numbers. And if you know this property, if you know that the real numbers satisfy this property, you can define this function to be this number. Okay, so this is already a slightly more precise, and this is not the way we will define this function later on, but this would be it would be possible to make this more precise. And in some textbooks, this is the actual definition. So like this, we can define 2 to the square root of 3, also 2 to the pi, and 2 to the other exponents, which are irrational numbers, and the same for a to the x, where x is an irrational number. Now, but for the moment, what is important for us is only the message about the graph, the property which the graph satisfies. So we fill the holes once more such that the graph of this function is getting increasing. Now, not in all cases the graph is increasing, as you know from high school. you know there are essentially three different cases. So in case where a is larger than 1, so for instance 2 to the x, the graph looks like this here. In case where, so this would be for instance 2 to the x, in case where a is between 0 and 1, you get a decreasing function, not an increasing function. So for instance, if a is 1/2, you get the same graph just reflected about the y-axis. So you have this graph here for 2 to the, actually this function here. And this is the second type, and the third type is if a is equal to 1, then you get a constant function. So this would be 1 to the x. So essentially you have three types, namely if a is between 0 and 1, then decreasing. If a is equal to 1, constant. And if a is larger than 1, increasing. Okay, and you also know that those exponential functions, they satisfy a couple of properties, which in our textbook are called the laws of exponents. So for instance, you have for instance, you have that a to the x plus y is equal to a to the x, a to the y. You have a to the x minus y is equal to a to the x over a to the y. So this is the first one. This is the second property. You have a to the x to the y is equal to a to the x times y. And you have a b to the x is equal to a to the x, b to the x. Now, you should realize already here that if we want to prove such properties, strictly prove them, it's easy to prove them if in case where, for instance, x and y are integers. But because of this awkward definition, okay, we said we fill the holes for the irrational numbers such that the graph is getting increasing. It would be quite awkward to prove. It would be not complicated, but quite complicated to prove such properties. So from here you already see that the definition you have seen is not very good, okay? Because you cannot precisely prove such properties unless x and y are rational numbers. In this case, everything is okay. Now, from these properties, you already see that, for instance, if you look at, please tell me if I erase too quickly, because I'm not used to having such a blackboard, and this blackboard seems to be made for people much taller than me. Now, if you use this property, you already see that if you have a base which is 1 over a, then you can write this as a to the minus a, which means that if you have the function 2 to the x and you want to have the function 1/2 to the x, you just get it by reflecting it about the y-axis. Okay. So you see already here some properties. Okay. Now, I guess you have learned most of this in high school, and you have already discussed many properties of this function. The most striking property of the function 2 to the x, or in general of an exponential function where a is larger than 1, is that it grows, that the function grows very, very quickly. In particular, if you compare the growth of such a function 2 to the x with the growth of the function x squared, then you will discover that this function grows much, much quicker to infinity than x squared. In particular, this function grows much, much faster to infinity than any power x to the n. So no matter how large you choose n, if you this is called a power x to the n. And if you compare the growth of this function with the growth of this function, no matter how large n is, this function here will grow faster. Now, I will a little bit later. I will show you this by using Maple. Maple is a very good program for calculus. In particular, Maple can do everything what you will learn in this course. Now, the good thing about Maple is that you can have it for free from our department's webpage, and I suggest that everyone is going to download it. I will use this program frequently throughout the course. I guess there will be an introduction maybe in a couple of weeks, not in my course, but there will be another 1 hour introduction into Maple, and I suggest everyone to visit this introduction. Another possibility to learn more about Maple is, you know, maybe we have 3 extra classes belonging to calculus. You know this, right? In Chinese, they are called 学班. There are three classes. Now, 2 of them are lab classes. In the lab classes, more or less what students learn is Maple. There is a 3rd class which is more directed towards theory. And the 3rd class, because of some problems, they have to shift the time, is not full yet. So you can try. If you are more interested in mathematics, in basic things, more interested in theoretical things, I would suggest you try at least to take this course, which is certainly helpful. It's just 1 hour, so every week, so it will not be a lot of work. But if you are more interested in mathematics, the theoretical part of mathematics, it's good to take this class. Now, because there is only 1 class, and also the number of students who can take it is restricted. But if we see that there are many students who want to take this class, it might be possible that there will be one more, that we add one such class. So just in case you are interested. Now, I will show you a little bit later how fast this function grows by using Maple. So in this course, you will learn Maple kind of online. So I will show you how to do it. And the best thing to learn such programs is just by trying around. So essentially, the way I will do it, I will not prepare the Maple sheets. So I will come here and I will plug in all the comments, and you will kind of learn it automatically, or at least some basics by seeing how I do it. Now, you know that such exponential functions have many applications. You know the most popular applications are normally as an easy model for population growth or radioactive decay. You will find this in our textbook. I just say a few words about one of these applications. I guess you have learned this in details in high school. So one example would be population growth. Now, for instance, consider a population where the number of individuals at time 0 is equal to, let's say, 50. Okay, and you know that the population will double every hour. Okay, so the population size. Okay, so from this you know that after 1 hour you will get twice the initial population. And then after 2 hours, again, the population size will double, and you go on like this. So this is quite naturally in such an application, the exponential function will show up. So you get, in general, that n of t after t hours is equal to 2 to the t times 50. And so in such easy models, if you want to model, for instance, the population growth of the population on the Earth, okay, you can use such a simple model. Of course, this model is very simple, okay? It's kind of its application is restricted because it doesn't take into account, for instance, if you think about the population on the Earth, that the Earth's place is restricted. Okay, so here the model will predict you that the population is growing and growing, but after a certain threshold for t, this will not be the case anymore. So this is one example, population growth. Another example is radioactive decay. You will find the example of radioactive decay in our textbook. I'm not going to say more about this. Now, you maybe have learned in high school, I guess most of you, that there is one exponential function. So we saw a to the x depends on a. There is one choice of a which is very important, namely you choose for a the natural number. Okay, so if we look at, just to motivate this, I'm not going to define the natural number at this stage. It's much too early to give a precise definition. But if you consider the function 3 to the x, it might look like this here. So this is 3 to the x. And you consider the function 2 to the x. Now, what you can do is you see that, for instance, for this function 3 to the x, you see that at 0 you will have a tangent. Okay, we will define tangent later on. You know this word, tangent? Okay, so you see that this function at 0 has a tangent. Okay. Of course, this is something you see from the graph, okay? Later on, we will discuss, okay, how to, just from this expression, 3 to the x, without looking at the graph, okay, how to see that a function has at some point a tangent. Here you see at 0, you have a tangent. I'm going to draw it. Okay. Now, you know that if you have a line, okay, an important quantity for such a line is the slope. You know this word? You all know this word? 斜率. Okay. So, you know that both of them have a slope, okay? Now you can use some graphing device, okay? You can plot the function by hand, 3 to the x. You can plot the tangent, and you can, just by measuring distances, you can figure out, okay, what is roughly the slope of this tangent here. Now, for this tangent, you will find out that the slope is, I denote the slope by m. So m is roughly 1.1. And for this function 2 to the x, you will figure out that the slope is roughly 0.7. Now you see something, okay, you could guess that maybe there exists a base, okay, such that the tangent at 0 has slope exactly 1, okay? And in fact, there is such a base. So there is a number a such that a to the x at 0 has a tangent with slope 1. Now, this choice of a is very important. And this a is called natural number. Okay, so we call it E. So E is defined as the base a with a to the x as a tangent at 0 with slope 1. Now, you have learned this in high school, right? Most of you, right? Everyone. Now, you know already, okay, this E is called natural number. So, of course, the obvious question here at this point is what is so natural about this number? Okay, it doesn't seem to be very natural. In particular, if you look at this definition, it doesn't seem to be very natural. This is a little bit from here at this stage. It's like maybe from high school you have already some experience, and maybe some of you already know why this number is called natural number and why we prefer this number, why this number is so important as a base of the exponential function. But at this stage, this depends on the way we define the exponential function. It's not so clear why this number is called natural number. Now, maybe you have also heard in high school that this number here, e, which is roughly and so on, is irrational. We will prove this. Pardon? We will prove this maybe next semester, that this number is in fact irrational. I guess nobody has ever seen the proof. For this number, it's quite easy to prove that this number is irrational. Okay, so for now, this is enough. We will accept this as a definition, but you should realize at this point, and this is what I have talked last Monday. Okay, that high school mathematics is quite university mathematics is quite different from high school mathematics. You should realize already at this point that actually this is not a precise definition. This definition here has several problems. Okay, namely. The first problem is, okay, we do not know whether this function has actually a tangent at 0. Okay, this is the first problem. The second problem is we do not know whether there really exists such a base such that the slope becomes 1. We do not know it. Okay, so this is something you have to accept at this stage, which is not precise. Okay, and if you want to know, okay, how to do this precisely, you have to be patient. We have to wait maybe 2 months, and then I will define once more the exponential function, but in a precise sense. And then we will see we will also see what is so natural about this base here. Okay. Any questions? Now, okay, if there are no questions, I just want to spend a little bit of time to talk very quickly about inverse functions. This is section 1.6 in our textbook. Now you have learned this in high school, but this is just to once more review what you have learned, just very quickly. What you have learned about inverse functions. Now, you know that by this here we denote the inverse function of a function f. So in English we read this y is equal to f inverse of x. Okay, and you know the meaning of this. If f is mapping x onto y, the inverse is mapping. If f is mapping y onto x, then the inverse is mapping x onto y. Okay. Now, we also know that not for all functions we have an inverse function. What you need is the notation of 1-to-1. So a function is called 1-to-1 if x1 is not equal to x2, then the image will be also different. Now, the importance of such 1-to-1 functions is those are the functions which have an inverse. Okay, in our textbook we have the so-called horizontal line test, which is a possibility to check whether a function is 1-to-1. Namely, you look at every horizontal is this, horizontal line, and if every horizontal line meets the graph of a function f, intersects the graph of a function f in at most one point, then the function is 1-to-1. So f is 1-to-1 if every horizontal line intersects with the graph of f in at most one point. Okay, so you know this from high school. So just to stress some examples. So if you, very easy examples. If you look at the function y is equal to x squared, then this function will not pass the horizontal line test, because if you choose, for instance, this line here, this line is going to intersect the graph of the function in 2 points. So this function is not 1-to-1, but if you look at the function y is equal to x to the cube, then this function is increasing. So an increasing function, of course, automatically passes the horizontal line test. So here, no matter how you choose a horizontal line, the line will intersect the graph of the function in exactly 1 point. So this function is 1-to-1. Now, already here you know that, okay, this is a matter of what you consider the domain. You know this word, right? Domain and range. Okay, the domain of a function, just for those who are not so familiar with the English words, is where the function is defined, and the range are all the values taken on by the function. So here, this function has domain R and range all numbers from 0 to infinity, the positive non-negative numbers, real numbers, and this function has domain R, range R, all real numbers. Now, here you see already, this actually, whether this function here has is 1-to-1 or not also depends on the domain. So if the domain here of this function, if we just consider positive x, then the function indeed is 1-to-1. So actually, to decide whether a function is 1-to-1 or not depends on the domain of the function. If you change the domain, maybe the function is getting 1-to-1. And as I said, the important thing about 1-to-1 functions, that's why you discuss them in high school, is that those are the functions who have the inverse. So we have the following definition. Okay, so let f be an 1-to-1 function with domain A and range let's say B, then f has an inverse. The inverse of y is equal to x if and only if f of x is equal to y. And here you can choose any y in B. And the important thing here that you have something like this, that there is only one possible choice of x, is this property here, 1 to 1. If the function is not 1 to 1, you might have more choices here for x. Okay, but for a function, the function value of every number has to be unique. Now, you have learned this already in high school. This is just to remind you. You also know, okay, that the important thing is about one basic property of inverse functions is that the domain of the inverse function is the range of the original function, and the range of the inverse function is the domain of the original function. So domain and range will exchange their role, and you have what our book is calling cancellation equations. Okay, so you have that if you first apply the inverse and then you apply the function, then you get y for all y in B. And if you do it the other way around, if you first apply the function and then you apply the inverse, you're back to x. This actually is the very definition of the inverse. Any questions? Now, I guess I don't have to do examples here. In our textbook, you also have examples, okay, how to find the inverse. Normally, you know this is very easy. So if you have, I mean, it's not necessarily very easy, but for functions where you can do it, it's very easy. So for instance, if you have the function y is equal to x to the cube plus 1, then you know, okay, you can you take plus 1 on the other side, and then you take the third root. So this will be the inverse function, and then normally you exchange the role of x and y, and that's it. So that's the way you can find inverse functions. But this works for some examples, not in all examples. For instance, if you have the function f of x, a little bit more complicated than this one, x to the 3 plus x minus 2. Okay. Now, in this case, you will have a harder time to find the inverse or to find the formula for the inverse. Indeed, it's possible. Okay, it's possible to find the inverse here, but the problem is you haven't learned how to solve such an equation. Now, one way you can do it is you can look at the graph. Actually, you have to understand also first whether you have to restrict the domain. And if you have to restrict the domain, what is a domain? What is a set A such that this function becomes 1 to 1? This is what you have to understand first. Also, this is maybe not so easy just to see from the expression here. But of course, what you can do is you can find some function values of the inverse you can find immediately. For instance, this one. For instance, so you can easily find some function values of the inverse without really finding an expression for the inverse. Finding the expression would be more complicated. Now, let's maybe just briefly recall the graph of an inverse function. Okay, so we saw already if A is mapped under F onto B, then B is mapped under the inverse onto F. Okay, so from this you see that the pair AB is an element of the graph. Maybe at this point, this is just a detail, but I should stress that the graph for us is also a set. Okay, not only what you draw. This is also the graph, but actually it's also a set. Okay, the set of all such AB. Okay, that's why I can write this. So that this point is in this set. Okay, so this makes sense. If and only if BA is in the graph of the inverse. And from this here, you see already how to get the graph of the inverse function from the graph of F. You reflect it about the line y is equal to x. Okay. So if you have some function and you have to find the inverse, the graph of the inverse, what you do is you draw the line y is equal to x, and you reflect the graph about this line. So you do something like this here. Okay? And then you get the graph of the inverse function. This you see from this simple property here. This is already, can be already quite useful, because from this you see already that if f is increasing, the inverse will also increase. You do not have to write anything down, okay? Just from this reflection principle, because this reflection principle here will preserve the increasing property. So if this function is increasing, this function will be increasing as well. This you already see here. Okay, now we just briefly recall some important inverse functions. First of all, you know the inverse of the exponential functions is called the logarithmic function. So this is just very briefly, so inverse logarithmic functions. Okay, so we want to find the inverse of the exponential function. Now you know that if a is not equal to 1, then f of x is 1 to 1. Why? What is the reason for it? Because the function is either increasing or decreasing. So the function has a monotonic behavior. Every monotonic function is 1 to 1. Now, okay, so if a is not equal to 1, then this function is 1 to 1, so it has an inverse. And you know that the inverse is called the logarithm with base a of x. So a to the y is equal to x. Okay, you also know that because if you look at the function, at the exponential function, the domain is R, the range are all non-negative real numbers, all positive real numbers, sorry. You know that from this you know that the domain of the logarithmic function are all positive real numbers, and the range will become all real numbers. Also, you can immediately find from the basic relationship between the graph of a function and the inverse of the logarithmic functions, the graph of a logarithmic function. So if, for instance, the graph of the function looks like this, then you just use our reflection principle. So you see that the graph of the inverse function will look like this here. So this will then be y is equal to the logarithm with base a of x. And also from this here, you get already some properties. I already stressed that this function grows very, very quickly. So from this reflection principle, you will get that this function grows very, very slowly. Okay, so this function will grow faster than any exponential function, and again from this reflection principle you get that the function will grow slower than any power function. Okay, so this is nothing new. You also get from this the law of what our book calls the law of logarithms. Okay, so you have some basic laws like the logarithm with base a of x times y is equal to the logarithm with base a of x plus the logarithm with base a of y, you have the logarithm with base a of x over y is equal to the logarithm with base a of x minus the logarithm with base a of y, and you have a similar property for the logarithm with base a of now b to the, or let's say x to the r is equal to r, the logarithm with base a of x. Okay, so you also have those properties here. Okay, so we are still discussing logarithmic functions, inverse functions of exponential functions. Now, we have seen already, okay, there is a special choice for a, namely you choose the natural number. If you choose the natural number, you get also a special logarithm called the natural logarithm. So if you choose a is equal to e, then the corresponding logarithmic function with base e now of x, quite frequently we use this symbol here to denote it, ln of x. Now, in fact, for us, this will be the most important logarithmic function. From the basic reflection principle, we immediately see one property, namely, okay, so this is e to the x, and this function here is the natural logarithm. Now, we know that the number e was defined in such a way that the slope of the tangent at 0 is equal to 1, and by this reflection principle, you immediately get that also the slope of this tangent will be equal to 1. This is one property. Now, as you know already from high school, actually, one logarithm would be enough. So you don't need so many because they are all interrelated. Okay, you have this, what our textbook calls the phase of change formula. Change of base, not base of, change of base formula. Now, of course, this is something you know. You can, if you have a logarithm to any base a of x, then this is equal to ln of x over ln of a. So from this, you know actually one logarithmic function is enough, okay? Because all others are just the constant times this logarithmic function. The reason why we use more is because convenience, okay? Now, just very roughly, this, of course, is a trivial result. All of you are certainly able to prove it, but just to show you once and also to explain how I'm going to prove in this course. Okay, so we just use the definition of the logarithmic function. So by definition, a to the y is equal to x. And now we apply the ln on both sides. So you will get that, from this you get that y times ln a is equal to ln x. And then from this you get that y is equal to ln x over ln a. And you have already the result. Now, whenever I show you a proof in this lecture, I will finish the proof by making something like this here. Okay, this is the usual notation in mathematics, and this will tell you the proof is over. Okay, so if you, some proofs you later on more complicated ones, I don't expect, because you are not mathematicians, I don't expect that you understand all details. But this is for those students who are more interested in the theory, more interested in mathematics itself. So for all the other students who lose somewhere in the middle, cannot follow the proof, at least they know when the proof is over, when I do this here. Okay, it's the usual notation. If you read math textbooks, you will see this all over. Now, okay, so I guess no question to this. This is very basic. Now, just to talk about one more class of inverse functions. This is just to remind you the so-called inverse trigonometric functions. Okay, so you know the trigonometric functions, sine, cosine, tangent, cotangent, and so on. For instance, for the function f of x is equal to sine of x, we will use the primitive definition you have learned in high school, the easy definition. So how have you defined this function in high school? The usual definition, you see, the simple definition is that you look at the circle, the unit circle, you measure x in so-called radiant measure. So if you have angles, you have different measures. One possible measure is the radiant measure. So you measure x in radiant measure. And if you have, for instance, so if this here is x, okay, then you know that the length here of this line will be the sine. And the length here of this one is the cosine. This is the definition you see normally in high school of the trigonometric functions. Now, also this definition is not so convenient in some sense. In particular, if it comes to, if you ask me the question, okay, how the calculator is doing it, how does the calculator compute this function? Now, obviously, the calculator will not draw a circle and then draw this line and then measure it. The calculator will use another method. Next semester, we will learn how the calculator is computing these trigonometric functions, which will give you another way to define it. But for us, this definition is enough for trigonometric functions. Now, from this simple definition, you already know how the graph looks like. Okay, so you start at 0, for 0 is 0, and so on, and then you move the whole thing. Okay, then you get something like this here. And once you have done one turn, once you have completed one turn, everything will start new. So you will just get the same. Okay, now you see already from the graph that this function is not one-to-one, hence does not have an inverse unless you restrict the domain. Okay, and there are several possible choices to restrict the domain such that the function gets one-to-one. Now, the standard way to do this is you choose, here you have pi half, here you have minus pi half. So the standard way to choose to restrict the domain is using the domain from minus pi half to pi half. Then the function gets one-to-one and has an inverse. The inverse function is called the arcsine function. Okay, so I use sometimes this notation here, or sometimes I just write sine minus 1x, and x is from this. Okay, x becomes the domain of this function, of course, becomes the range of this function here. The range is from minus 1 to 1, and the range of this function will then be from minus pi half to pi half. You get the graph just by reflecting the whole, this graph here about the line y is equal to x. You know all this from high school. And then you can do the same for the cosine. So also for the cosine. Now, the standard way, again, the cosine is not a one-to-one function, does not have an inverse unless you restrict the domain. And here the standard way to restrict the domain is you use from 0 to pi. You have here pi. So you just look at this piece here, and you consider the inverse of this piece here. And the arc cosine function, or the inverse cosine function, is then the inverse of this function with this domain here. Okay, so the range of the inverse cosine function will get 0 to pi. The domain will get from -1 to 1, and so on. And then you can do the same for the tangent. For the tangent, you have to restrict from -pi half to pi half. And you have also a couple of other trigonometric functions. You have the cotangent, you have the cosecant, and you have the secant. And you will find the definition in our textbook. I'm not so used to the secant and cosecant because they are not used in Europe. They are coming from the American system and are used here in Taiwan as well. But actually, as you know already from high school, one trigonometric function would be enough because they are all related to each other. And I guess you have spent a lot of time to learn some of the formulas, some of the relationships between those functions. But actually, to define one would be enough. The reason why we define so many is because of convenience. If you have more functions, it's easier to do computations. Maybe to do one exercise, because this is an important class of exercises which will show up again later on. You find, for instance, in our textbook, you find this exercise. Now, the most easiest way to solve something like this, of course, is using the calculator. But if you want to do it without the calculator, the most easiest way is by looking at geometry, simple geometry. You see that, okay, if you just look at the argument, you see that theta is equal to the arc sine of 1 over 3. And by definition, this means that the sine of theta is equal to 1 over 3. Now what you do is you use a right triangle. Okay, because you know that the sine, so if this is theta, you know that the sine of theta is the length of this side here over the length of this side here. Okay, so you just use this here, so you see it's 1 over 3. Okay, but you can easily compute the length of this side here by the theorem of Pythagoras. So you see this is 2 over square root of 2. And what you actually need is the tangent of theta. Okay, and for the tangent, you know that it's this over this, so you immediately see 1 over 2 square root of 2. This is the easiest way to solve such an exercise. Of course, you could also use some relationships between trigonometric functions, but this is maybe more complicated. We will need the same. We will need this much later when we talk about integration. So this basic idea, and we will maybe also in the assignments. We will have some assignments where you are asked to do this. Okay, so any questions so far? This was more or less the chapter 1, which was just the introduction. Now we go on and define, we want to define precisely a limit. Limits you have considered already in high school. Maybe you haven't seen yet the precise definition of a limit. Before we go to the precise definition, I just want to maybe talk a little bit about some reasons as to why we need a precise definition, and also at the same time review some basic things about limits. So we will go on to, this is limits. So this will be section 2.2. I will afterwards, I will not follow strictly the syllabus, so I will go then on, after section 2.2, I will go to section 2.4, and then I will skip back to 2.3 and so on. But first let's talk about a few things from section 2.2. Now, in section 2.2, there is, we will not give a precise definition of the limit. We will discuss limits maybe, I don't know how you do it in high school, but we will do it maybe similar to how you have done it in high school. Now, just to start with an example. This is a very easy example. So f of x is equal to x squared minus 2x plus 4. Okay, so once more, the most important thing is you have to be patient, okay, because I know that you know much more about limits than I assume at the moment, but you can, for the moment, you can forget everything about limits, okay? So let's use the point of view, okay, that we have learned nothing about limits. Now, originally, how did we, in mathematics, how did we find the notation of limits, which turned out to be an important notation? So one thing you can do is you plot the graph of this function. Okay. It's better to, of course, it's better to have a graphing device for this, roughly like this here. Now, you see that, okay, here you have, this is maybe 1, this is 2 here, and here we have 4. It's not like this. This is not true here. It should look like this here. Okay, now you see that what we are interested in is a question, okay, if we fix the 2 here and we want to approach 2, and we want to understand, okay, if x is approaching 2, what is the function value doing, okay? Now, if you look at the graph here, or if you use your calculator, you try some x values close to 2, okay, you will recognize that if you get closer and closer to 2, the function value here will get closer and closer to 4, okay, which is actually just 2 plugged in. But the new thing is that we try to approach 2, okay? We approach 2. No matter how we approach 2, we choose values which are close to 2, okay? Evaluate f and look what is f doing. And the basic observation is that as x tends to, is getting closer and closer to 2, f of x will get closer and closer to 4. And this is already the notation of the limit. Okay, so we will write for this the limit of f of x as x tends to 2 is equal to 4. Now, this is not a definition, okay? This is talking around, okay? This is not a precise definition. We will, a little bit later, I will give the precise definition. But before I come to the precise definition, I will tell you that, I will show you some examples where you will see that actually, if you have a more if you have such an easy function, it's quite easy. But if you have a more complicated function and you just rely on your calculator to figure out such a relationship, okay, in some examples you might not be successful because the values which the calculator gives you are wrong, okay? So this will also motivate why we need calculus in order to compute such limits, okay? Now, the first thing maybe to stress here in this limit definition is that x is close to 2 but not equal to 2, which means that the function f of x, this function is defined at 2. But the function must not, if the function is not defined at 2, this is no problem, okay? So for instance, if you look at this limit, sine x over x as x tends to 0, okay? If you just plug in 0, you get 0 over 0, okay? So the function is not defined at 0, but still you can consider limits, okay? Because the limit notation tells us that x has to be close to 0, but not equal to 0, okay? Now, again, if you use here a calculator, or if you plot the graph, you will figure out, okay, this is equal to 1, okay? We will later on see how to prove this. You have seen this certainly already in high school. Now, here maybe, because in the limit notation x is not equal to 2, okay? So functions which are differently defined at 2, okay, will still have the same limit, okay? This is a basic principle. So for instance, if I do not look at this function, but I look at a slightly different function, which is x squared minus 2x plus 4, if x is not equal to 2, and 100 if x is equal to 2. Okay. Still, if we consider the limit of f of x as x approaches 2, we will get 4 and not 100. Okay. Now, so here you see that this is essential. Okay, that I tell you that in this definition, x has to be not equal to 2. Okay, because otherwise here you would get something different. You would just plug in and that's it. Okay, now maybe let's turn to a more. So at the moment, the only way to find limits, okay, because we forgot everything what you have forgotten everything you have learned in high school. So the only way at the moment, okay, we can find limits is by using your calculator, okay, or by plotting the graph and then looking, okay, what is going to happen if you approach some number. Now, I just give you an example to show you that if you just rely on your calculator, the guess for the limit you get might be wrong. Okay. You find in our textbook the function square root of t squared plus 9 minus 3 over t squared. Now, for this, I will show you Maple, and this is also a good opportunity to explain you how to use it. Now, Maple has also a programming language implemented, so you can do a little bit more. Here, actually, I just look at this function here, and I compute certain function values. You see here, this is the parameter x1, so I start with, when I goes from 1 to 6, so I start with 1/2, and then I go on to 1 over 4, 1 over 8, and so on. And I compute 6 function values of this function here. I have to. Maybe I can explain just this basic, some basic fact about Maple. Every comment you plug in has to be, the last thing has to be a semicolon, okay? If you forget the semicolon, then you do not get any answer. So you see here of every comment. But this is a program, so it's a little bit different. But if you just plug in a comment, you have to end it with this here. You can also end it with semicolon, but then the answer will not be displayed. Okay. So if I change this to a semicolon, you will get the same. Maple is doing the computation, but not showing me the result. Okay, so here you see now we are interested in this in the limit of f of t as t tends to 0. Okay, we are interested in figuring out, okay, what happens. And you see the function in particular is not defined, okay, at 0. But then no problem for the limit definition, because t has to be close to 0 but not equal to 0. Now, I'm computing here some values for, so you see some values for t. T is getting smaller and smaller, and you see the corresponding function values. Of course, you know from high school how to do the computation, how to compute the limit here. But this is just to stress the point that you are not always successful just by using your calculator. Okay, here you already can get a guess. Okay, you already will get a guess what the limit actually is. Okay, namely you see here from the last line, okay, that the limit seems to approach 0.166666 and so on. Okay, so 1/6. Now, let's do some more computations. So maybe let's add a couple of computations. Okay, now you see. If you just do the first 6 computations, okay, you might get the impression that the limit is 1.666, but from the 7th on, it seems to change again. Okay, so the last one, you see, the 6th one is 1.666624, but then the digits, one of the 6 is changing again, and then also the previous digits are changing again, and then suddenly you have 0.13, then suddenly you have 0.26, and then you have 0.0. Okay. So just by doing these computations, it looks like, okay, as you make the t smaller and smaller, okay, the function value is approaching 0, not 1/6. And this answer is wrong. And the reason is, the reason I'm not going to explain, because this is another class, okay, this has to do with numerical mathematics. But from here you see that it's not just enough to rely on the calculator, okay, to do such computations. Now, we could do the same by plotting the graph. So maybe let's try to understand this function by plotting the graph. Because from here we see, okay, our guess, something strange is happening. Okay, if we plot the graph, okay, so this is over a certain range. So I go here from the same function, and I plot the function from minus 0.1 to 0.1. And again, from the graph, you get the feeling, okay, if I approach 0, okay, so the value which will be approached by the function is 1/6. But the very nature of the limit is that you have to make the range here small, okay, because you're interested in a small range. Now, again, let's make the range smaller and smaller. Okay, so let's make it already very small. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, this is not good. 4. These are too much. Okay, so here. Now you see something very strange seems to happen at 0. Okay, but this, what you see here, okay, is a problem of the of Maple, a problem of the calculator, okay, and it has nothing to do with the function, okay. So the main message from here is you cannot really rely on your calculator or on such software, okay, to figure out such limits. And we have to develop, there is a need to develop methods to figure out some such limits, okay? Otherwise, you could say, okay, why do we have to learn this now? Because we have software, okay? We just use the software, that's it, okay? But from here, you see, it's not possible. But actually, of course, Maple is able to compute this limit. I just show you this, okay? You can use this limit comments. Then you have a square root of t squared plus 9 minus 3. Over t square, d square, t is equal to 0. Okay, so 1/6 is the answer given by Maple also. Now, but once more, the main thing, that's why I demonstrate is that you shouldn't always trust what your calculator tells you, okay? And it's better here to develop some machinery in order to find out such limits and not just to rely on some experiments. But of course, for some limits, if you do not know what the value should be, okay, the first step would be to try out some values, just to plug in some values and to make a guess, okay, sometimes the first step, okay. But this guess, as you see here, can be wrong, okay.
So you're saying that on Monday